do this. Okay, so we're, I think, good to go. So I want to finish up that derivation today. It's only Pete here, so I just kind of stare like Pete during the entire time. So, oh, and everyone came. Oh, it's just going to be Pete. I was just going to stare at him and make him uncomfortable for the entire time. Oh, okay. So I'll just stare at both of you. But I can get him stare at both of you like this. Okay, so I want to finish up that derivation. But then we want to start doing practical things. We want to start making things. And we're going to start making a circuit. And I think you'll enjoy the circuit stuff. It's going to be certainly a lot easier than some of the stuff we've been dealing with. So that said, let's finish up that derivation. So what we did last time, we said we had an electric dipole. And an external E field. So tell me about an electric dipole, we call it P. What's the direction of P? From what to what? No, it goes from the negative to the positive. So I have a negative charge here and I have a positive charge here. The P always by definition goes from the negative to the positive. So this is a P. Now what about the magnitude of this? What did we say the magnitude of this thing is? So this is minus Q, this is Q, the distance is D. The magnitude of P is by definition. Yep, it's going to be just one of the charges. Don't put in both because then you get 0. Times in the separation distance here, D. That's what you have. Okay. And the claim is that if we have a magnetic field like that, if we have an electric field like this, so this is some sort of external field, and if this is P, what is that external field going to do to that P? Yeah, it's going to take that P and it's going to align that P with the E field. And we said it's going to do that, it's going to put a torque on it. So the torque, and I stated this last time, why are there 4s on the 4? There's one there, there's one there. Yes. Crazy. Okay, so what did we say the torque is given by? Yeah, P cross T. So what we want to do is we want to do that derivation today. And it won't be too long. We did one little review piece. Did a review on torques. We said that if here's a little stick, the pivot here, I put a force here F. And if the distance from the pivot to that force is R, what did we say that torque is given by? So it's going to be the R. We're going to call X cross because it's a cross product. Okay. We said if you look at the magnitude of this, the magnitude of this is what? It's just this magnitude of R here times this F sine of theta. What did we say this F sine of theta is? This is F, this is theta. What is F sine of theta? Okay. Remember this we called F parallel. This is a part of F parallel to the R. And this is F perpendicular. It's the amount of F perpendicular to R. But this is parallel, the amount of F parallel to R. This is the amount of F perpendicular to R. Which of these causes the rotation? This guy. And so we said the torque, the magnitude of it is this moment arm, magnitude of R, times this F perpendicular. So we're going to use these ideas and we're going to prove this, and then we start circuits. Okay, so proof. Okay, so I'm gonna have an E like this. I'm gonna assume it's constant. It doesn't have to be like this. Like, well, for no reason I'm drawing it this way. This is E like that. And here's my little dipole. No, I'm going to call this here D. Okay. So what would be the force on this guy here? How's F connected with E? Times Q. Remember, your E is up over Q, so let me get this. So this is the force on the positive charge. This is Q times E. What about the force on this guy over here?
Negative.
It's negative, exactly, and going this way here. So this F minus will be this Q times E like that. Now, where's the, so what's going to happen here? What's going to happen here? Where'd my stick go? Here's my stick. So here's my little stick. So I'm gonna, if I pull this way, then pull that way, that's gonna take this stick and actually align it like this. That's why the E field takes the P and aligns it with the field like this. That's why it does that. Now, let's calculate the torque. Where's the pivot on this guy here, do you think? What? Exactly. The pivot's going to be the center pivot. And so I can take this force here and I can go like this. Call this theta. So here's my F parallel and here's my F perpendicular. And I can do the same thing over here. I'm going to erase this because it's going to be kind of hard to see it. Put it up here. Go like this. This is my F parallel. This is my F perpendicular like this. So if I look at my torque on this fellow, the total torque. So let's look at the magnitude. What's the direction of this torque here? Is this up, down, right, left, and out? Tell me the direction of the torque in this guy here. I'm getting it out. Hey, Aaron, why is it called a right-hand rule?
Darn it.
It's easy to do. It's really easy to do. You take your right hand. This is my R, right? R goes from the pivot to where that force is applied. R is this way. The force is this way. R cross F. The torque on this guy is into the board. And so how do you write something into the board? So this guy here should be like that. I'll call this torque plus because it's on the plus charge. Pass into the board. What about on my negative frame here? How does, yeah. Okay. We're going to do the R cross F because that's the torque. Okay. So let's do the R cross. Take your right hand. So the R, so let me redraw this part. So get this guy here. And here's your R for that guy. Okay. And then here's your F. So let's do that. So you take your fingers here first. You point them along the direction of R. So any orientation like that. Right, because my fingers would be pointing in this direction. Right? Anything like this. Right. Make your hand, not go on this way. Make your hand look just like the board. Okay, so anything like that, my fingers would still be pointing in the direction of R. Now you have to bend them in the direction of the force. You bend them into the direction of the second vector. So you can't do the following. I can't do R cross F because that hurts. I can't do R cross F because that hurts. Instead, I have to turn my hand like this. So it's R. Now go up, R. And F is that way, cross F. And then your thumb goes in like this. That makes sense? What do you know about a cross product? This had better be both R and F. Exactly. Good. Now tell me about the torque on this guy. So this guy's going to be R. I'll put a little plus here. This will be R for the -1. Here's the F for the minus one. How does that torque go? Up, down, right, left, and out. Is this guy? I'm getting it out. Yeah. How does this go? Up, down, right, left? Here's your R, here's your F. So let's do it. So R goes, so any orientation like that, and my fingers don't know, may take your hand and it's going down, so make it go down. It has to look just like the picture. Now, what do you have to do? You have to bend them into it. So if you wanted your thumb to go out your R, you'd have to, that hurts. So what do you have to do with your hand? Exactly. You have to go like this. So it's R, crossing off your thumb is going in. So this guy is also, so the torque on this negative side is also going into the board. So they're adding, that's how the thing rotates. So they're going opposite directions and rotate. They'd cancel. So these are just going to add. It's going to be the torque on the positive charge, plus the torque on the negative charge. Okay. Now let's just go through and beat it out. So let's do this guy. So this is going to be R plus times F perpendicular plus. That's this guy. And this guy is going to be plus R minus times F perpendicular minus. Well, what is this distance right here? What would that distance be? D over 2. I go like this, I go like this here, this is theta. I know this magnitude here is QE. So here's my F perpendicular. So what would this guy here be? It'd be this side times, I need this. This is the hypotenuse. Here's my angle. This side is the opposite because it's opposite that angle. So this side here is your F positive, force on the positive charge, times your sine theta. This gives you D over 2 here. This guy here is F on the positive charge. Plus, now let's do this guy. What is my R minus? Yeah, so this guy here, that's D over 2, because this right here is my R minus. If I come over here, here's my F perpendicular minus, here's my theta. What is this guy? Opposite of that angle, so keep going. So you said the sine of theta is the opposite of the hypotenuse. So then if you solve the opposite, what do you get? Well, you're right there, you almost have it. Okay, you just take over the hypotenuse, and so this guy here, this guy, would be this F minus theta. That's what this guy is here. This guy right here is just your hypotenuse times the sine of theta. Yes.
Just like a review question.
Yep.
But, so we don't break it up into components because they're both perpendicular.
What do you mean breaking up? What do you mean breaking up into components? We are breaking into components. You mean that in
just
terms
like
of,
torque in general. I
So-
used the wrong word.
okay, so with torque, you're breaking it up into component, you're breaking it up into a part that's parallel and perpendicular to your moment. That's why they're not a normal X and a normal Y. You can break them up into parts parallel and perpendicular to R. Because the torque is, by definition, it's that, the R part, the moment arm, times the part of the force perpendicular to this R. That's the definition of a torque. Now this R, and then this perpendicular part here is the part that causes the rotation.
If the torques were going in different directions, then would you split it? Or-
Yeah, okay, so if the torques are going in other directions here, so let's say it's not, well, let's say you had this. Then what would happen here? This would be R cross F, this would be coming out. So you have one being positive and one being negative, and then they'd cancel each other.
Okay.
That makes sense? Okay, others? You haven't done torques in a while. Yes.
We are accounting for the negative part, but that's negative.
Yeah, so the way we've accounted for the minus sign here is the fact that if this is a negative charge, that force is going to the right, I mean to the left, and that's how we've accounted for the minus sign. And then that torque will be the same direction as this one. That's why the thing is rotating.
Okay. I mean, sometimes it's just hard to visualize that it's already been accounted for.
It is.
in a weird way.
Yes. Okay, that's, yes. Signs are really, really hard in physics. Okay, so what happens here? Well, this guy here, we're almost done. This is G/2. This magnitude here, that's just Q times magnitude of V. Sine of theta. Well, this is G/2. Well, this is that same force as that Q over the magnitude of V. Sine of theta. What do they do? Try again.
Okay.
Yes, they are. Okay. So you get dq magnitude of V sine of theta. Hey, does this have a name? That's your magnitude of P. So you have magnitude of P. Magnitude of V sine of theta. Well, that's nothing but the magnitude of P cross P. That's your net torque. That's your torque. So your torque is by definition. Well, it's not definition, we proved it. P cross T. A very practical equation. We'll come back and look at that later. When you go to magnetic fields, we're going to get the exact same thing happening with magnetic fields. But instead, what we have is something called a dipole, a magnetic dipole moment. And that'll be the entire basis for NMR. So for NMR, we're going to basically put something in a magnetic field. We're going to do something to the magnetic field, and we're basically going to flip the protons. We're going to flip their spin. And that's what you're going to be doing in NMR. You flip proton spins. That gives you something really profound. Questions? Okay, so that's kind of that end there. Now, so that's kind of like the theoretical aspect of this. Now, what we're going to do, we're going to take what we have, and we want to start applying it to make things. So what we want to start making are now circuits, because now we have a theoretical foundation for actually doing things. So let's apply. Our knowledge to practical devices. The first thing we're going to do, we're going to deal with something called a DC circuit. So the first thing we're going to look at DC circuits. Okay, what does the DC stand for again? direct current, and we're gonna see what that means. So this means this DC part means this means there'll be circuits with DC batteries. Now there is going to have things like this. This is a symbol for a DC battery. So we need a couple of terms here. Well, yep, it's like the same thing. That's just a symbol for it. Okay, so what I want to do is I'm gonna make my little, before I actually do everything with a symbol, I'm gonna go back to my little battery like this. So here's my battery. I'm gonna put a wire here. So here's wire. Okay, what did I tell you you can think of a battery as being? Why do we call this positive? Why do we call this negative? It is, but this positive, I told you to always think of a battery as being something. A battery is a source of an electric field. This is a source of an electric field. Everything's going to happen because of that electric field. So that means that this electric field goes like this. This is how electric field goes. That's the E field. Now, let's ask something. Suppose you're a little electron here. If you're a little electron here, what would be the force on you? If you're here, what would be the force on you? The electric field's going that way. Yeah, there's going to be a force on this electron going this way. That would be the force on the electron. What's it going to do? It's going to take this electron, move it over to here. It goes here, then what happens at this point? Some incomprehensible chemistry that makes no sense. It's over here. I'm not trying to make fun of the chemist, but if you go over there late at night, okay, you'll see basically a big cauldron there. It'll be a pentagram, and they're all going to be wearing robes, and you're going to be chanting Latin backwards. There's going to be these tentacles coming out of it, and then batteries come. That's just FYI. Okay, so the electrons didn't go over on this side here. Then what did they do? So they go here like this. And so if you could watch that electron, what is it going to do for the rest of its life? It's just going to go like this. All that electron is going to be doing is like this. Okay. So we have actually charge that's moving. And we have charge that's moving, you call that current. So you're going to have continuous electrons. As long as the battery keeps on doing what it's supposed to do, the electrons will continuously move a counter clockwise fashion. When you have moving, question? Okay. When you have moving charge, you call that current. Whenever you have moving charge, you have current. Well, we define it in a certain way. current I, so current I is by definition it's the amount of charge that passes a given line and the amount of time. Let me draw a cartoon picture of this. So this is an imaginary line. What's going to happen? In a certain amount of time, there's going to be a certain amount of charge that goes through. So delta Q here. This will be delta Q is the amount of electric charge. That crosses the line, crosses the line. And the time delta T. So somehow, let's say you could see electric charge. You have your little stopwatch, you start it for some amount of time, so there'd be a certain amount of charge that crosses this line. You take that amount of charge that crosses that line, you then divide it by how long it took to cross it, and that is by definition your current. This is a defined quantity. Does that make sense? Let's get the unit through this. Okay, so what do you measure delta Q in terms of? The amount of charge. The amount of charge will be measured in coulombs. The amount of time it takes to cross is measured in seconds. Okay, a coulomb per second is by definition 1 amp. Okay. If you had 1 amp going through your body, you are basically electric. Okay. It takes on the order, if you were to have like a milliamp going through your body, you're probably in serious danger. It doesn't take a lot of current going through your body. What does current do actually through your body? It's kind of neat. Well, it's terrifying if it happens. It screws up your heart something. I mean, it's going to mess up your electrical signal. I mean, it goes through your brain, your brain is shot. But if it goes through your heart, it's actually going to cause the heart to kind of go like this or clamp up. If you're getting electrocuted, get electrocuted with a lot, because that's going to cause your heart to clamp up. And if somebody's around, they might be able to revive you. If you don't have enough going through, it's going to cause one of these motions, and that's going to rip your heart muscles all apart. It's going to be quite dangerous. But it doesn't take, it takes on the order of like milliamps to cause the damage. When you have to be, let's say you happen to be an amateur hobbyist and you like making circuits, and this actually turns out to be a lot of fun. What kind of voltage do you want to start paying attention to? About 40 volts. When you start getting around 40 volts or higher, start paying attention to what you're doing. You can start causing some damage. When you're below that, you're probably not going to hurt yourself. If you start getting closer to around 40 volts or higher, that's start paying attention to what you're doing. Okay. Now here's the weird thing. Okay. So the electrons are actually going like this. Okay. Suppose instead positive charge moved. So let's say the negative charges didn't move. Let's say instead positive charges moved. Which way would the positive charges go? So let's say the protons moved, not the electrons. Let's say the protons moved. If you're a little proton here, which way would you move? Yeah, you would actually be moving this way. Okay, so this is actually how the current would go. Okay, here's the weird thing. And this is, the convention is stuck and you just have to deal with it. Historically, people thought that actually the positive charges moved. They didn't realize it, they didn't have any understanding of atoms or anything. So they thought the positive charges moved. So everyone thought that the actual current would go like this. And everything is stuck with that. So when you draw one of these circuits, you always assume that you have positive charge, and that you then draw the current going this way. Okay? So you always assume, so even though the electrons are, the electrons cause current. The current in a circuit is always drawn, and it is always drawn as if positive charges made up okay? Does that make sense? Now, let's actually look at that wire a little bit more. So if I could, here's my little battery again. I can draw a really thick wire here like this again. I'm going to kind of look at a little cross section right here. So let's say here's a little cross section of this wire here like this. That's all cross section of the wire. So the electric field is going to be going like this. So here's E. I'm just looking at this section right here. If you look in there, what would you have? You'd actually have, let's say this is copper wire. You'd actually have all these copper atoms here. So these might be copper atoms. So if you're a little electron here, what are you actually doing? What would be the force on you? Yeah, you'd be going this way. You'd be accelerated this way. But if you're accelerated this way, what are you most likely going to do? Smash into a copper atom, right? You're going to smash into a copper atom right here. And then what are you going to do? You're going to basically recoil, then get reaccelerated this way, and smash into this one. Then what are you going to do? You're going to reflect. You're going to basically recoil, come back, get accelerated this way, smash into this one. Recoil, get accelerated, smash into this one. Recoil, maybe get smashed into this one, then this one. You're not going to move in a straight line. That little electron, if you could spray paint it and watch it, it's going to have all these little things here, and it's going to make this kind of jaggedy motion like this. It's going to kind of move like this. Okay. These electrons, the flow of the electrons are impeded by basically the copper atoms. So the flow. So the E field accelerates the electrons. But the electrons collide with the atoms in the wire. The collisions with the atoms in the wire impede flow of electric current. We give this a name. We call this impediment to electron flow. We call this resistance. This impediment to electron flow. It's called resistance. And is measured in units called ohms. The units for ohms, units for resistance, the symbol for ohms is capital omega. Do not use lowercase omega. You always use capital omega. You always use capital omega. Yeah, you can, but everyone, you just, everyone uses this. I'm going to show you how you make, we're actually going to have a lab on Friday. It's going to be kind of Simon Says. I'm hoping to give us all each a multimeter so we can see how it works, and resistors, and we're going to make things. We'll probably do this for a couple of weeks. This is fun. It's a very practical skill to be able to have. Okay, so a couple more things. The resistance in a circuit is symbolized by the electrical symbol. And basically, it's the spring symbol from what we had in the first semester physics. So if you had a circuit like this, remember here we said here's our circuit. You're not going to keep on drawing this circuit because that's just too hard to draw. So we need a way to basically to write this symbolically. The way we're going to write it symbolically is the following. We know how to do this. Okay, so what's this guy here? Okay, so that's this guy. Okay. And then what are we going to do? We're going to say that this wire here has resistance. So we're going to represent all this here by that here. Then I can have wires connecting here like this, but all those wires really have nothing. They're just connecting. They don't have any resistance. So the way I'm going to represent this is this. Is this plus, this is minus, I can go like this. Show me like that. This circuit here is going to be represented by this. Here's a battery. This represents all of the resistance in the wire. So I've drawn wire here, like this. Here's wire. Here's wire. This wire, any resistances that this has, I'm treating this as having no resistance. Any resistance that would have, I'm dumping into this right here. So this right here is a symbol for this circuit here. So this right here is this symbolizes this right here. Does that make sense? This right here is a simple DC circuit. This is the simplest DC circuit. How would you draw the current? If I said draw I for this, how would I go? Remember, the electrons really go like this. But we don't assume we have electrons moving, we assume we have positive charge. So how do you draw the current? The other way. So you actually draw it like this. That's actually how you draw that circuit. Now, the reason why it's a circuit here is that you have to have a closed loop. This basically means a closed loop. All right, so here I have a closed loop. That allows current to flow. Okay, if let's say I had a switch in here. Let's say I had this circuit. This right here, this is a switch. If that's open, what would be the current? Yeah, the electric field wouldn't be able to loop all the way around here, so you can't have current. So this would actually have no current. And you'd call this an open circuit. So something as an open circuit, it means somewhere you've broken the wire and you're not having current to flow. That's what it means to be a current, an open circuit. Now, what do you think it means to short something? If you short out a circuit, you have to be careful with this one. What would happen if I came over here? I put a little wire connecting these two like that. How will my current go? It's going to go like this. You might have some going through here, but primarily it's going to go through here. It's going to bypass all this other stuff. That's called a short. The problem with the short here is that this is a good way to create a fire. I show you remarkably fast. These little circuits here, if you can take a DC battery and just like a tiny little wire on it, that wire is going to get ridiculously hot. I mean, really, really hot. You wouldn't think of a dumb little, 5-volt battery with a little wire connecting the two. You wouldn't think it would do anything. That's going to get preposterously hot. I mean, enough that it can actually start fires. But that's what it means to short a circuit, and you have to be careful with that. Now, why would these things get hot anyways? So why, if you have current flowing through a circuit, would it get hot? Let's draw the picture of it. So here's our little wire. Here's our electric field. Here's our atoms. This is just our little cross section of a wire. Here's our little electron. What's this going to do? It's going to come, get accelerated here, smash into this one, get recoil, get accelerated to here, here, here. It's going to do this jitter motion. Every time this electron hits an atom, what's it going to do? It's going to cause it to vibrate. You can think of the atoms here as being really kind of connected by springs like this. This is how you can view the atomic bonds. This is actually how you can kind of view the lattice of a metal. So that electron comes along and smashes into here. This is going to cause this to vibrate. That'll cause this one to vibrate, and it's going to recoil and smash into this one. Every time it collides, this thing causes it to vibrate. Well, what does vibrational motion cause? Heat. So this thing is going to heat up actually quite bad. Is this a good process to have? Do you want metals to heat up, or do you not want metals to heat up? I give you a hint, it depends. Where would you want this to heat up really, really quite a bit? And you may have used it, you might be using it every day. What? The heater. Okay, so in heaters, you want this to happen. In particular, let's say you want to make a coffee maker. Okay, what do you want to do? Well, you want to send current through some metal. You want this process to occur, but you want the metal strong enough that it doesn't melt. But you want that metal to get really, really hot and then boil your water for your coffee maker. Let's say you have an electric stove. You turn on an electric stove and how it has those metal stove tops. What color do they turn? Red. Why? Because this process here is occurring at a really quite a lot, a significant rate. And that's actually starting to glow. That's how hot it's getting. And that's a good thing. You don't want that to melt. Okay, but you want that heat to then go into whatever you're cooking. Yes.
So is there some sort of limiter being put on it so it doesn't spontaneously close?
Oh, yeah, they have there's tons of, when your stove is more than this. there's a whole bunch to it. But you have to make sure it doesn't. I mean, and you can vary that depending on the thing. You know, you have the little controller, and that's all controlled. Does that make sense?
Yeah.
So sometimes you want this to occur, sometimes you don't. Where don't you want this to occur? Okay, anywhere where you don't want to lose current, because basically this is energy loss. In a case like a stovetop, you want the energy loss because that energy loss is going to cook your food. So that's a boiler you want. So you want that. And something, let's say when you're transmitting this power from, let's say, NICEAG up in Rochester or GD up in Rochester, you don't want this to occur in the wires because if this is occurring in a wire, this is powerless and you're not recovering that. So you're actually losing energy. So whether this is good or not really depends on where it's occurring in life. Some places you want it, some places you don't. Okay? Does that make sense? So what we're going to do tomorrow is we're going to start looking at this. And we want to start hooking these things together and seeing what kind of objects we can make. And we can do a lot of really kind of neat things with this. So what we're going to say is, we're going to say, well, okay, maybe I have this guy here, maybe here's a resistor. Or maybe I have another resistor here, another resistor here. Maybe I have something like this. Maybe I even have another battery. I can look at a more complicated circuit. And we want to start analyzing more complicated circuits and see what kind of things we can make. Okay. Yes. Questions? Okay, have a great day.